Hi guys, today we want to finish off the characteristics of transition metals, which is the catalytic properties. Okay, this is almost the final one actually, but one more just to deal with the stoichiometry of the complex ions. Now they will ask you about the difference between a heterogeneous catalyst and a homogeneous catalyst. Very frequently asked. The heterogeneous is reactants. Remember, it's the reactants and the catalysts are same phase. Phase or state, okay. So heterogeneous is different phase, sorry. Hetero means like heterosexual, different, isn't it? Okay, different phase. Normally is solid, right? Normally the catalyst is solid, okay? And the reactants normally is a gas. Just like, for example, Haber process. Haber process, N2 plus 3H2, this gas and gas. Okay, reversible you NH3, gas, and 2. Here normally is iron, Fe. Remember, it is a metal, okay? It's a metal, not an iron here, metal, right? So this is a heterogeneous. And homogeneous, of course, they are the same phase. This one normally is both are equals, okay? You see later, this is the one that they will always give you, this one here, okay? This is called peroxo disulfate. Now it's called persulfate iron. It's a very famous one. Remember, you must know how to use this from your data booklet as I showed you before, right? This fellow is a regular gas star. Okay, you can see S2O8. Okay, S2O8 2 minus. Okay, right? This fellow here. It will accept electrons. It's an oxidizing agent. This one is a very common oxidizing agent. Okay, now let's look at first the heterogeneous catalysis. Now, how does it happen? They don't expect you to know in detail. We used to study in detail actually. First of all, remember now this is the surface. Can be nickel, of course. Here, I put in nickel because we normally talk about this reaction here. Right, this is your electrophilic what? Addition, is it? Right? Of what? Of your alkenes. Okay, with hydrogen and nickel is supposed to be the catalyst. Okay, catalyst here. Remember, it's a solid, it's an element. Okay, it's a metal. Okay, why do transition metals and ions can act as catalysts? Well, it's really because they have these empty orbitals or partially filled empty or partially filled d orbitals. Okay, orbitals that can accommodate the electrons, the electron pairs. Okay, of the ligands, right? Of the reagents, right? To form what? To form, we call this reversible dative bonds, okay? Right? Dative bonds. So, like for example here, these are the surface, these are empty orbitals of your nickel, or in this case of your iron. So the ethene, right? See here comes in here, right? Now this double bond here slowly breaks, then slowly form, okay? Right? It's a ongoing process and form what? Dative bonds here, okay? And the hydrogen also came here. As it comes near the surface, it forms dative bonds here. And this one partially break. And of course, another hydrogen here, okay, with another, this is a nickel here, forms the dative bonds here, so slowly break. So here, slowly break, and of course, here slowly form, here slowly form, they will form like that one. And here sort of break and form, and then they form the whole ethane, sorry, okay? And this one will break to form this side, some will go this side, some will go this side. So you form, now this is called chemisorption, right? First, of course, it's called diffusion. That means it will first, of course, is diffusion. They will diffuse onto the gas will diffuse onto the surface, okay, on the surface. It's a surface reaction, surface of the TM, okay, right? It's, remember the solid, right? And then chemisorption, right? Surface TM has lower energy orbitals and can interact with molecules, okay? So the molecules, which means the can be N2 or H2 or whatever, get absorbed. Not absorb. Absorb means to go inside. Absorb means on the surface, right? Absorb. And they form what? Reversible dative bonds, okay? With the empty d orbitals, right? Right? And so this will create an intermediate, or what you call an activated complex, okay? Activated complex, which is of course complex, which has the lower what? Lower EA, okay? So easier to happen. After the bonds are formed and reversed, then they undergo desorption, okay? Right? Number 3, desorption. That means the product goes away, right? So this is a whole thing, which is a surface reaction. Now I'll show you how they answer this question, okay? There's a question here in page 74, which is, asked for 2 of them. I'll just show you some first, okay? Now here, by using iron and its compounds as examples, iron very common, okay? Right, you can see this in Haber process, you can see it in your benzene with iron to go to electrophilic substitution, right? You can see S2O8 minus with your Fe2 plus Fe3 plus, okay, with I minus, okay? So this is why they use iron here. Outlines different modes of action, homogeneous and heterogeneous catalysis. This is interesting. This question came up twice, right? 2 years, right? And same thing. It's very well, seldom they ask like the essay question, 8 marks, and my goodness. Okay, so I don't know, sometimes they just come up in the blue, is it? Right? So here you can see, choose 2 examples. You want to underline 2 examples. One, and for each example, it means 1 for heterogeneous, 1 for homogeneous. State what kind of catalyst. So state the catalyst first, whether it acts as homogeneous, all these are marks, no, catalyst, homogeneous marks, and write balance equation. So 3 things are supposed to write. Okay, now let's look at the marking scheme, right? This is the, okay, sorry, the question here. Now here, see, heterogeneous, right? Okay, heterogeneous what? Okay, they just say different states, okay, which means what? The reactants, reactants, you better put down this, okay? Reactants and catalysts have different states, okay? And homogeneous, 2 1 mark only. Homogeneous, same state. Okay, it means the catalyst and the reactant same state. Okay, right. So the first one now, first one, of course, the correct allocation of terms heterogeneous and homogeneous common to catalyst. Okay, the first time we put heterogeneous. Okay, heterogeneous. So you put heterogeneous first. Okay, see here, and Haber process. 1 mark for this. No, if you say heterogeneous and Haber process, 1 mark. Okay, right, and of course use the equation, right. N2 plus H2, you put gas here, just in case they are very fussy about it. You could put here Fe, what? Solid. Okay. Right? How can this work? See now, all they want to do is the catalyst works by absorption of the surface. That means the reagents get absorbed onto the surface because they form what? Reversible what? Reversible what? Dative bonds. Okay, you put the whole thing easy right? Okay, which forms what? Which forms a low. We have a lower EA. Okay, show them you know the stuff right? And then once it's formed, they will diffuse. Now this is called chemisorption. Chemisorption. Remember they are adsorbed. Adsorb, not absorb. Okay. So this 3 marks. 1 mark for heterogeneous, 1 mark for the process, okay, and 1 mark for the equation, and 1 mark for how they are absorbed. Okay, now let's go to this part here, okay? All right, on this part here, this is more, you need to explain more, okay? This is, this one come out twice already, very tricky as well. Okay, 67, Oh, this is 67. Now here. Okay, for this one here, homogeneous catalysis, where reactants and catalysts are same phase. Normally, as this is aqueous. Okay, normally it's aqueous. So the reason why this homogeneous can occur because the TM ions. Why is it ions? Because it's aqueous. What if it's metal? Cannot be aqueous, isn't it? Right. So ions. which means it's a positive 2, normally positive 2 and positive 3, because these are both what? Very common, and they are what? Very easily reversible. And you can find +1 +3 very common in your data booklet. You just check and see. Right? You can see here from cobalt, right, what's now? Okay, see cobalt 2 plus 3 plus. Okay, yeah. Okay, chromium 2 plus 3 plus. Yeah. Okay, right. Iron, of course, 2 plus 3 plus. Right, it's very common. Right, Mn 2 plus 3 plus. Okay, right. You can go and refer to it yourself, lah. Okay, nickel don't have, nickel don't have. Okay, tin. Okay, 2 plus 4 plus. Okay, so what I'm saying is 2 plus 4 plus, 2 plus 3 plus are very common. So the reason why they can act as catalysts because the easiness, right, to have alternate. That means that the oxidation can shift up and down. Okay, so they can help. The key is in redox reaction. Yeah, redox. The homogeneous, the heterogeneous catalysis not redox. They just form an activated complex. But here it will have the redox. Because to go forward and backward, to go forward is oxidation, to go backwards, right? It's reduction here. So it means they go forward and backwards. So here we can see this is the main reaction. Okay. Right now, let me show you the names. The names of these fellows here. See now here is called persulfate ions. S2O8. Persulfate ion. Now you know all. I got an old question here, which is a pretty good question here. See now, it's called peroxo disulfate. This was the one I'm no used to. But now mind, it's the same thing. S2O8 2 minus is peroxo disulfate or per disulfate ions. Okay, aqueous solution here. So these two questions will give you a key. Let me explain the theory first. Okay, right now remember in this equation here, this reaction here, peroxo disulfate S2O8 2 minus and I minus here, they can react to give you sulfate and I2, which means that you get here will be your yellow solution. Okay, yellow solution, or you can say a black solid like you want to say. Okay, because I is black one. Okay, but it forms a solution rather because I2 plus I minus give you I3 minus, which is yellow solution. Okay, it forms a complex ion here. So remember from here to here, I can say is what, right? It will accept 2 electrons to give you your sulfate, right? Right, like here. Like here, well, like here, this is one of them. This is the original one for here. This is the original equation from your data book. Okay, and of course, I minus to go I0 is oxidation. So one is reduction oxidation. This is a redox reaction. Okay, now by itself, you can see by itself this can occur. What? See now, right? Now remember, this is your E0 value. You check. You don't believe me, right? Now here, S2O8. Okay, plus 2 electrons would be plus 2.01, right? See here, plus 2.1, and of course it's undergo reduction here. Okay, now here of course I'm quoting the original I2 plus 2E. Okay, it's a reduction one. I2, it's I2 here, right? See now, I say, yeah, right? Reduction is there. Plus electron go here, plus 0.454. Okay. But of course, to see whether it react with what, you need to write it out differently. So this one, this undergoes reduction, okay, plus electron. This undergoes oxidation too. Okay. So I minus will go to this one here, right? So you put the whole thing down here, right? You change the sign. You get plus, so it means S2O8 2 minus plus 2I minus can react to give you I2 plus 2SO4 2 minus. Yeah, okay, can happen. Why? Positive sign one, right? Feasible, isn't it? But they're very slow. They ask you the question here. See? Okay, this is the first question they ask you, which come in what year? This is 09, right? See? The reaction between iodide ions and persulfate ions, S2O8 2 minus, is slow. Slow. Can happen, slow. See, whenever a reaction is slow or cannot happen, right, it's about the activation energy. Okay, high EA. This is a very common answer. High EA. Okay, so the EA is blocking the reaction, right? So why is a high EA? The reaction can be speed up by adding a small amount of, see, Fe2 plus, oh, no, and they don't put two together. This, all this, or you either start with Fe2 plus or Fe3 plus. Why? The following reactions take place. See, now if you start with Fe3 plus, normally Fe3 plus, because see, of here, see now, right? You choose from here, Fe3 plus, okay, right? So Fe3 plus will accept electrons. That means that it will act as an oxidizing agent. Yeah, okay, right? So it will oxidize something. So who will oxidize in these two here? Who will get oxidized? I minus R. So I put the first one first. So if I use two I minus go to I2, why not? And then Fe3 plus by electron. That means I choose this one and this one here. So now that's the two reactions here. Why not? I'm just doing out here. Okay. So I minus is here. Fe3 plus here. Why not? I find out. Oh, the E naught values can see is plus 0.23. So this is plus, put red. So you can work it out if you want to, just to prove to yourself, okay? This will be plus 0.23. That means what? Feasible. Feasible. Okay, that means, right, it's feasible. Second one, of course, now the Fe2 plus here will act, see, it needs to be recycled, isn't it? So a catalyst will participate in the reaction, but it will be reproduced or regenerated at the end. So Fe2 plus will go to Fe3 plus oxidized by what? By acting as a reducing agent. So this fellow here. Okay, now here, this one here. All right, go to here. Fe2 plus will give electrons to this one here. Okay, the two electrons here. So this one here is plus 2.01, and of course, this one here, the reverse is how much? Reverse says your minus 0.77. Okay, now, okay. So you can see it still give you a positive sign here of plus 0.19. Plus, that means what? Feasible. Okay, so you can see that this one here, so it's plus 1, 2, no, it's plus 1, 1, 2, 4, yeah, 1, 2, 4. Okay, plus, that means it's feasible. Right, so now these two, see, the reaction can speed up by adding a small amount of the front reaction. That means these two will occur. Why this type of catalyst is occurring? Why? Okay, why this type of, because why is homogeneous. See, marking scheme. Okay, see, sorry, this is the question paper. Okay, down here, not this one there. Down here. Okay. Because why? Why is happening? Because of the homogeneous catalysis. Okay. Sorry. It's on here. It's on here. Okay. I've put some marking. Okay. Red, homogeneous. Okay. Right. That's number one. Okay. What type of catalysis occur? Homogeneous. Okay. Homogeneous. Okay. Rates 2 and 3 are faster than equation 1. Now this is equation 1, right? Why is faster than this? Well, because in here, well, they are both of them are positive charge, so they repel. So even collision theory, they must collide. So they must collide harder because it's come together, repel, cannot come together. So higher energy, higher temperature, they come together anyway. Okay, so because of the resistance here, so. Reason why, because you can see here, right? Yeah. Sorry. Yeah. Okay. Homogeneous state, correct equation with terms. Oh, sorry, this one. Oh, this one. Okay. Ions in 2 and 3 are oppositely charged, so there's attraction. But for ions in number 1 is similar charge, so there is repulsion. Therefore, higher EA. Okay, so that's why, right? Now, so in this case, the foreign pathway shows the enthalpy flow. Now, the question is here, they say, oh, no, I know, Fe2 plus or Fe3 plus. So which one do you decide to do first? If you want to talk about I minus first, right? I mean, you need to start with Fe3 plus, right? You talk about S2O8 first. Then you use what? Fe2 plus. So the choice is up to you. So in this case here, right, in this equation here, It's not moving at the moment. Now here, so this is the original, this is I minus, this is SO2. Okay, now this one, which we're going to start first because you need to talk about the intermediate not here. Okay, so if you start with Fe3 plus, which is the original, that means this will undergo reduction. That means under oxygen, that means you get I2, you know, I2 Fe3 plus, and of course plus the unreacted S2O8, 2 minus. You know, okay, so this lower EA. This is the original EA. Okay, this is the EA. You have to overcome the 2 negative charge. This is the original EA. This is a lower EA. Okay, or rather here. So here, this is your EA1. Okay, right. So now Fe3 plus here, another charge here going down. Don't know how high or how low, they didn't tell, so you don't know lah. So come down here. Okay, so now we have this one here to come plus what? Fe what? 3. You start with Fe what? Fe oxidized, I can't forget. Okay, Fe3 plus, so this is Fe2 plus, isn't it? Fe3 plus, let me see, plus 1 electron. Why not? Okay, so it's Fe2 plus here. So. Okay, so here's Fe3 plus. Yes, okay, so I can see the marking scheme, right? This one. So, okay, you just want 2 humps, 2 continuous activation energy humps. Here and here, okay, and stop here, or can do one, okay, here. They don't care how high this, but they didn't say. As long as this end is lower than this one. Okay, so the same thing here. They don't care what you put here. This will be activation complex. Okay, 2 continuous humps, 1 mark, both less than original. Okay, this one both less than original. Okay, both less than original. This is original. Starting and finishing at same points. Okay, same points. Okay, starting same. Okay, so you start here, you end here for either one of them. So 3 marks here. Okay, now let's look at the other question. Right, the other question is quite challenging. This is not very challenging. This one here. Okay, this is an old question. Iron 3 plus catalyzed reaction. They tell you it's iron 3 plus, which means remember the Fe3 plus here plus electron reversible Fe2 plus. It's very important to actually use equations from your data booklet because it's a reduction one. So always go to reduction. And I tell you what after, okay? Peroxide disulfide S2O8 2 minus. Okay? Okay, this blah blah blah, quite simple. Okay, it's of course your homogeneous. Okay. By considering relevant E0 values from a data booklet below described, explain the role of this one here. All right, very simple, isn't it? Right. So you can do the 2 things. Right. So here cell marks here. So like here you can start by doing here. Right? These 2 things. Okay. You can either start this one first or this one first. Can do. So they ask you, well, if 2, but they ask you 3 plus, then you must start the one first. Okay. So sorry, this is 1, 2. Supposed to they say 3 plus. I just forgot. See, you need to be very sharp. Okay. That means you start with one first. Start with 3 plus. Okay. Which means it will attack the V should be over here. Sorry. Okay. 3 plus start with attack the one first. And after it's formed, then this is formed, then this number 2. Okay. Right. So the 2 reactions are there. Right. This is how you answer the first part. Right. Now, then it say also, the second one, also by base of E0 values, this is the original one, choose 2 other examples of transition metal. Okay, ions, they want ions. Why ions? Because it's homogeneous, I don't know, cannot metals in, must be ions, remember? Ions. They can predict and they can be predicted to act as catalysts. What others? What other factors might prevent the ions of the choice? So how to solve this problem? Okay, now the key word, the key thing is, let me just show you. Okay, wrong one. We did it all up here, so it's easier for you to see. Okay, all right, now here. Okay, now remember, wait first, let me just pause this for a while. I forgot where I put the thing. Okay, so how are we going to choose? right? What substance? Okay, now remember, always look at the electropotential table here. Okay, that means you're going to choose from here the transition metals. If you choose one by one, it's going to be very difficult. Okay, so you have to choose, like, the E0, right? Between what and what. Okay, now remember, so that you can have a window to choose from. Now remember, okay, now the E0 must be coming from here, so it's easier. So the E0 must start with the table, and of course, in this case here, you need to start what? You need to start with your iron 3 plus here. See, iron 3 plus. Okay, see now. So in iron 3 plus, this is plus electron. That means this is E0 from where? From your data polarity. So it's plus 0. This must be the starting point. So now remember, it will have to react with I minus first, because this one plus electron. So this is an oxidizing agent. You oxidize one first. That means it's the first reaction. That means that if for this reaction to occur, right now, this Fe2 plus here, the whole thing here must be positive. I'll put red color, okay? Positive. Positive. That means the E0 here must be, remember this is the fixed, this is fixed on. Minus 0.54 is fixed because it's I minus 1. So you must have something here, iron or cobalt or chromium or whatever, they must have a value that is bigger than minus 0.54. That means that it must be positive. That means your X, your E0 here, must be bigger than what? Plus 0.54. It's not, right? If it's less than 0.54, if it's plus 0.44, that means it's going to be negative, isn't it? Negative 0.10, that means negative what? Not feasible. That means your E0 must be bigger than this one here, right? Must be positive as well. All right. Why positive? Because you must choose the E0 from the reduction one. Means it must be plus electron. Plus electron means this the original E0 will be from your table, right? Now the second one here, if you were to reverse this one here now, iron, okay? When you reverse this, is minus 0.70, okay? That means that this value here must, because if it's minus, if it's more than this value here, you will get a minus sign. That means it must be less than this one here. Anything less than here, because see the E0 is positive 0.77. Here is negative. So that means your E0 here must be, if it's positive, it must be less than what? Positive 2.01, because reverse becomes negative 2.01, isn't it? So it must be less than positive 2.01, right? If it's equal, that means it's 0, so it cannot be equal. So the E0 here will be the reduction E0. You will follow your table. So it's very important to choose correctly. Reduction table. Okay, now 0.54 and 2.01. Now you choose. Okay, see now. Okay, 0 is your E0 here must be greater than 0, positive 0.54, and must be less than positive 2.01. That's not. Let me check again. I get messed up. Okay, all right now. So you go out. Okay, okay now. Cobalt. Remember, I can't take this one here because it is solid. How about cobalt 3 plus and cobalt 2 plus? Now remember, this is in the reduction. Yeah. Say good. Here 1 plus 1.82 is between here, right now here. So now this is now a substance inside here. But first, of course, we have I minus now. Okay, I minus. Yeah, I minus is reduction now. Okay, so cobalt 3 plus or plus electron, right? To go here, and it's positive. That means can react. Okay, and of course, if you do with S2O3 also can. S2O8, sorry, 2 minus, then we will plus electron to give you 2SO4, 2 minus here, and this one is positive 2.01. So if you reverse the cobalt, remember, cobalt 2 plus, right, here, going backwards, go backwards here, to cobalt 3 plus electron. So 2 here, and of course this will be the same. This is minus 1.82. You still get a positive value, isn't it? So this can, okay? This can, okay? And what is, okay? So the E0 value can. Now how about this one here? A chromium, okay? Chromium 3 plus, minus 4.1, cannot. Why? Because it must be, right, bigger than 0.454, cannot. How about How about this one here? How about dichromate? Dichromate, okay, famous, okay. Now, here's of course +6, here's plus, okay, +133. Can, isn't it? Because this is between here, +133, okay, between here, isn't it? Right? Is bigger than +0.54, it's less than 2.01, okay, so can, but cannot. Why? Because this fellow is negative. See that? So it must have the first one is the E naught, right? Reduction one must be between this window. And number two, it must not be negative, it must be positive ion. So there are two considerations for this question here. That's why I say it's quite a thinking question. Okay. So see here, this is an old question. So you go back and think, okay. So it says here, okay, right. They ask you, on the basis of E naught values, choose two other examples. So it's copper. Okay, let's choose two. Okay, so it's copper, cobalt 3+. Okay, now one more. Okay, let's look. Normally is Mn. Okay, Mn 3+. See now, is +14. Now is what is bigger than +0.54. Right, is smaller than +2.101. So this is the common one. Okay, right. You cannot use this one, even though it looks very tempting. See, this is also can, isn't it? Right? But why? Because it's negative. Okay. So they ask you to choose two. You want to go for more? You look for more lah. Okay. I got no time for that. Okay. Right. So here, what other factors you might prevent the ions? Okay. Well, the catalyst, right, must be number one, ions. Number two, it must have not be what? Not be negative charge. Okay, right? Must be what? Be positive charge. Okay, now. So now with that we end our catalyst for your transition metals. So I've got one more to go, which is your stoichiometry. Okay, I will do it tomorrow if I have time. All right. So goodbye and keep studying. Okay.